So one answer. Yes, welcome back everyone. So today for this we'll be running through your and if we have time, but we have time, work on the midterm that has been so we will set the bare bones later if at the wanna so, we'll be writing the code in MPS, right? We'll not be able to size it or split it, right? But that you get how to write a code. That's what we'll be doing here. Let's get I want to double. Let's begin. So for normal VHDL houses divided into multiple parts, but for our purpose, we'll look at the three basic parts. Look at the library, and then we'll also look at the entity. Then finally, we'll look at the architecture. So these are the three different parts of a VHDL file. So the library would like it's basically you including, like if you remember your C programming, not you done any programming, right? You want to include your packages, your libraries, the external dependency that you need. Right? Like you don't write code for like anything to run it, right? It's the compiler that must run it. You want to include any library, any code that someone else has written. You don't want to rewrite yourself, but include it as a library. Then your entity, what your entity is your circuit view from the outside, right? So you first look at your it as a black box, right? Now what is coming into it, what is coming outside, what is on top of it, everything. When you look at the circuit from the outside, right, you're not looking at the logic or the behavior, just looking at its output. When you consider like an entity, that's your entity. Your architecture will refer to the behavior or logical definition of the circuit. As you define your circuit as having two inputs, one output, A, B, and then Q. Your architecture will say that Q is actually equal to A or not B, something like this. Like this is what your architecture is saying. Architecture is describing behavior, how the logic is actually working with circuit. Now let's actually look at how to write basic VPN architecture. This is your library to include. So what you are working with is the IE library, right? If you decide not to, the IE library is standard. Let's go with that. With the standard library, that is with hardware hardware. This is, has some special data types that we need that will be used in logic, and those represent more specific situations that you. We'll talk about it more. Now let's look at the entity. How the entity is defined is to get an entity, you write an entity. So this entity name can be anything. So it's one, two, other, random, or circuits. You understand? It's something that you take variables and do it. Go to the next line, and then the keyword port here. Come back to what is actually inside the port. This thing you can it is practically like related to something more like C, create this and everything. Focus when you're coding. Understand? Now with your ports, can be anything. So you're going to put that is how your entity would look like. The architecture. Now, how is architecture written? Architecture is written with the word architecture. Then the architecture's name, right? So normally how I would like you to go about it is so that it's not for you A underscore, A underscore, A underscore. Then you talk about the entity, architecture of entity name. Understand? So now you look at architecture of. Now you have to talk about that architecture that you are putting in. To understand? Now you also come here to understand. Then so this is where the architecture actually go. So sometimes you can define some things or actually take architecture as a place talking about. We'll get to that one too. Just mentioning the back of your mind to end whatever you are. And underscore. This is how we would write it. Like basically, this is your skeleton. So that's what I want you to keep as you're about to. Now let's talk a little more about how it is written. How it is. Now VHDL first of all is not case sensitive, right? Meaning that you can exchange any of lowercase, uppercase, and then it will still be fine. VHDL is not case sensitive. Don't try and like with the way that you write your names and things. Feel free. As long as you can read it and it's maintainable and you are sure. So right now, I want us to go and go combinational circuit example. Let's just combinational circuit. A very simple one. I will give you a taste of language is all about how the have here. Now this is your circuit that this can all gate by the way. Now let's look at something. In a circuit like this would be would look like this. See? So this is how your entity would be, right? Fine. Everybody knows that A and B are inputs, right? The input signal. And Q is your output signal. Understand? Yeah. So kind of like this. So that's the circuit you have in mind, though. Like keep that model in your head. That's what you're about to implement right now. Now, when you look at the port there, what's your port? And here, by the way, this is a comment, right? After your two dashes, this is a comment in HDL. So feel free to do this. Now your port. So now we have two ports. One output. Now, how do we define something like this? So this is how it will go, right? We talk about it now name, put a colon there. Talk about direction of now flow. This is also like how would I describe this? This is template, yes, of how you should write your signal, direction of signal flow, then with STD logic. You understand? This is how we should look like. It doesn't look like this, then you start to know that there are problems. Now we know that A is a what? A is an input signal, input signal. So output signal. And now we are done. Like this is basically your entire entity. That was how simple it is. In this case, we will not need any. In this case, we will not need any signals or intermediate signals. We will not need that. So let's start with the beginning and end. Understand? So for this, how is your circuit going along, right? Wait, I have to thing always trip up. I don't let it trip up, right? For your last now, for your last one, don't put a semicolon there. Don't put a semicolon there. So come after the bracket to understand. Now let's begin. working with architecture. For this, you can describe the architecture as this, right? About A noted. So this bar here, forward. So you can write a Boolean expression. So we want to make it simple. The Boolean expression is equal to A bar plus something like this. Now you can describe that basically. So assign to a certain value, right? As what is what the index. This is basically perfect. And now you are done. Like this. You can put brackets around this for easier your maintainability. That's it. This is your computer circuit. It's very, very simple. Now then I'm going to run through some things that can meet. First of all, this is how combination circuits are. Right? HDL, the hardware synthesis language, right? But then what this means is that even though it describes hardware, it is still software, meaning that this thing is very important. That means that the order of your they're not important. They'll be executed at the same time. That's in mind. I don't hold intermediate values. If I was to do this, then assign Q, like let's say not A, then assign Q not B. First won't be evaluated. The second won't be evaluated. It doesn't hold intermediate values. So you not see the graph like anything. It's basically like that. Like you will just see it as not B. It is hardware synthesis. Next, have to mention object in VHDL. For doing electrical, although I try and get to important objects. Like we'll not talk about anything. We'll talk about the signal object, the constant object. Everything else is not important. There's also a variable object. You let's include that one. So a signal. What a signal, like a representation of a signal is basically a wire. Like, basically a wire. That's what the signal is in DHL. A constant is a wire, but it has a certain value. This wire, assume that this wire is one, like this. That's what the constant is, right? The variable would also a wire. The variable, sometimes it is a wire. It has a very, very weird to get into right now. Don't use variable. Not and then the constant will be fine, right? Let's say that have a circuit like once you present this value, right? This particular value is A and B. Right? But if you want to represent it, you can also place it there. Right? You can the signals represent it. So internal wires, internal connections that are not seen outside. Because if you look at the entity, the entity will only see A, B. So you don't see this value. You don't see this wire value, right? And so if you want to represent internal wire values, you can use signal, the keyword signal, right, for the signal object. Data types in VHDL. I'm rushing through, but I'm touching on the important. For the data types, one have normal one, the integer, boolean, bit, a bit vector. You already know this. An integer represents an actual integer value 1, 2, 3. Boolean, so this one you write it as 1, 2. Boolean would be represented as true or false. Bit, so now this is important. Right? Bit is represented as 0 or 1. Right? These are not integer values. This represents like a low, and this represents a high. So that's you can also use that, right? The quotes are needed, or it will be interpreted as an integer. Now, a bit vector is a one-dimensional array type. What that means is that you can have 0, 1. This is a bit vector. Understand? It represents some bits, but then we will use one variable name so that's easier for this one. Right. So now you have your VHDL operators. VHDL operators, you already know them, and or no those things like X or and not. I think that's a bit that the ones that must have like these are operators, right? They're supposed to you do bitwise operations on them. If I give you something like, so this is just an example, right? I give you something like 110,000, something like this, right? So this operation is a bitwise operation. We do 1 and 0, 1 and 0, 0 and 0. Then this will give you 0, 0, 0. Right? A 0, 0. This is a bitwise operation. That's what I mean. I think that's everything with so HDL basics. Now let's move into something that's very needed. Signal bus, very needed in HDL because it makes your code so simple. You wouldn't believe it. So signal buses. So a signal bus is basically a signal vector. That's it. How plenty different. That's basically it. So you have a vector of signals. That's it. That's basically it. Vector of signals. How you would apply this? Let's go to. This is how a signal bus is initialized. However, you use a keyword signal. Now you give the signal name. So colon to come inside again, right? Now st underscore logic underscore vector. Now the width has come to right. So if you have right, let me put it in a different line. That you can differentiate this way. So let's say that you have to initialize it to some certain value. Now you use initialize it to 0, 0. Now the width of your bus is 0, 0, 0. Now you see some important thing, right? Thing is that I'm using double quotes here, not single quotes. That means that this is a vector or a signal bus. You understand? It's very, very important to understand the difference between. Well, I'm not really sure how important it is, right? But that's a good that I've been. Now, so why is this important? And we look at the compact notation, right? Because yeah, you will see this when you are working on the midterm. Make the entire thing so simpler. Notation is simpler, and then your readability and your maintenance is so simpler. I know what how important that is. Now let's look at this width of this bar, right? How would you describe a width of something that is a bit long? What you do is 3 down to so something like this, right? Find it. Or you can use the keyword to or down to. And let me even talk about it, right? All have ways of all have like the ways that they affect most significant bits. So if let's say I use to let's use A so that's simpler. A down to B. What this means is that my most significant bit, my least significant bit, if I use A to my MSB, my LSB. So let's say that I do 2 down to 0. What that means is this is how the letters will be arranged, like 2, 1, 0. Again, so this is how it is. So 2 represents your most significant, 0 represents your least. How we define it. Hope you are getting it. No, just let me go over it again. Right? And vectors are accessed the same way, right? That's the way any programming language that you might. Right? your index. This is how you would access it. Because we'll get to there and then you how to access it. There are different ways of sending values and getting values to now buses. We'll talk about them about them. Now we're not working with a lot of code. Let's get to the break down first. Very, very important. We've talked about combinational circuits, right? Now let's talk about sequential circuits. Using where we're all here, right? Sequential circuits. How do we describe sequential circuits? So the thing is that sequential circuits, how do I okay. Let's start with the keyword process. Let's start with the process in VHDL. So the process can be described as, let's say, smaller subset of statements, or let's say subset of something for architecture to understand. Now, the important thing about it is that every process has a sensitivity list. Every process has a sensitivity list, right? Sensitivity list is a list of signals that activate that particular process if they change, right? So let's say that have a process A, B. What this means is that this process is sitting in somewhere, is lying dormant too. Right? But the second that A or B changes value, process will start, it will begin. Right? This is so important. Right? You can think of it as like an easier way for you to work with your clock. We can put mostly that's how it is, right? Process clock. And we place our clock here. It means that whenever the clock changes that, you implement something, execute some process. You can already think about ways that this efficient. Right? Yeah, like for example, we have to. Ashok, let's implement a deep clock or something so that we can wrap our minds around this, understand. Now, hold on for me. Okay, and about to. I was just told that wasn't clear. Hold on there. I have to put that time. Let's just try and get the basic. Let's move. Let's talk about it. Now, entity. Just let's talk in here. Goes with the flip flop. Understand? Now, for your input, right? How does a D flip flop look like? Let's try and so for a D flip flop, how it is? Right? You have an input, have a reset. You have kill, you have D, and then you have a reset, and also a clock. Yes, so everybody knows how a D flip flop works, right? Hold on for me. I'm sorry for the noise. I think it's just value. Whatever you supply to it, and the same value it will keep. Right? That's why it's called star. Let's give the data for you. So you have a D, you have a reset, you have a clock, and you have kill. This is your entity basically. Your entity, and this is an alternate way of writing your values that you can just cascade them together. If you have a D, you you have a clock, all like logic. Then you also have so how get the last one doesn't. So this is it. Right? You are done with your entity. So let's look at how it works. How does a D flip flop work? How a D flip flop works in this particular case is that you have a certain reset, right? When your reset is zero, when it is zero, it works normally. Your D and everything, your D comes on and your Q also come on. When your reset is one, it will force your Q to be zero. It doesn't matter what D is, right? It will force your Q to be zero. You can write the code like this. Have the value of D, have reset. They have a clock. Let's just include, not forgetting anything. Now, when your reset is zero, when your reset is zero, so your D can be zero or one. The clock can also be. Now, in this case, we are saying that it is edge triggered. Edge triggered. For if you remember, an edge trigger at the change, when you are changing from either low to high or from high to low, that's when your flip flop is actually in motion. You understand? Let's see that this is always correct. It's always correct. Now, when your reset is zero, is zero, this is one. When your reset becomes one, regardless of whatever D is, right? And regardless, no, we have to this the clock, sorry. This is the clock, right? Process it zero. To understand. So we're putting our truth table. Now let's implement it. There are a number of ways that we can do this. And the easiest way, right? The easiest way will be if and else. Right? We are getting close to exams, but let's just keep it like that. Let's use an if and else. Then So how do we what do we do now? Now the way that can do this, right? The way that we can do this, let's say with the if and else. The way that we can do this stuff is that process. And one thing I forgot to mention about the process evaluates statements in a sequential order. When you write normal VHDL architecture, as I mentioned there, it doesn't like it executes everything like parallel. There's no one which is better than the other. As for the process, the way of thinking about it is that evaluate it in also evaluate your first statement. So the order of the statement is very important in this case. Now there's let's not talk about it. It's evaluated. Okay. Now so can begin a particular process. As I said, this is important because we want it to something when the clock is rising. Right? When the clock changes, that's when we want it to also like want it to process to begin, or when the reset button has been hit. So this is called an asynchronous reset. Async. This means that at any point in time, the reset is pressed, value should go to zero. Doesn't matter whether the clock is on or off. You understand? That's an asynchronous reset. Not reset is that the reset occurs with clock. So that's synchronous and asynchronous reset. Some live in guitar system and you use your can go smooth. Have a process and you begin that particular process. Now let's begin. What when we begin the process, what's going to happen? As I said, the if and else statement. Now if first of all, right, if your if your reset fall through and as I said, like same thing, right? If the reset bet is equal to one, so that is the output, right? So basically ended. Now if clock is rising, it just as I said, as we mentioned, was edge triggered, it's not level triggered. You take the value of nothing thought about it. You have to end your if, then end your process. Also, processes can be given names, right? Processes can be given names so that you end them like that. So right now, this process, I can name it E, name it as if the name of my process. Then we can end the process. So now this we basically implemented. So now think about it. So if you're able to do sequential, you're able to do the sequential circuit. And what the basic the system, how we implement finance state machines are a little different. Talk about them at a time. We have a class of five. Let's high end something else. Let's look at the test benches. At the test benches. Like that'll be more use of our time than on the okay, so we look at the test benches together. Look at the test benches together. Let's look at the mid. Okay. So implementing pick one. I'll recap it when we are doing the next one. Implementing FSMs. You know. So a finite state machine is a machine. It's a machine, right? that has a finite number of states. Like you already know, machine that has a finite number of states. Number of different states you can be in are not infinite. They're finite. You can define it yourself. So how an SSM is defined, right? If you remember the millimole thing I did before midterm, millimole, how it is that, all right, finite state machine as this. And break it down into three options that it seems easier to your eyes quickly. So when given a statement that write the code in VHD or given that how implement it, that it seems way simpler to you. This becomes your output logic, becomes your next state logic, this becomes your register bank, memory, like well, however you would name it. Now this thing, right, your output logic will produce some output. In the case of our method, because Y out, it can be a number of outputs or one output. This that's have output logic. Your state register. So now what your next state is doing is that your next state is dependent on your next state provides input to the state register. I produce the next state, then it will the state register. We'll all look at how this thing, like how this will be modeled to fit our midterm question, right? Now let's look at it. The next state logic will produce a next state. Now we pass on to your state register. The state register would produce, like will lead it to it. So your state register will take it to the output logic because your output logic, why out can be dependent on what your state is. Then not like it can. It is dependent on what your state is. Then your next state logic too, right? Is dependent on what your previous logic was. Then finally you have input. Then your state register is powered by a clock. There's no one but the clock. Now this is it. Now your next state logic is the combinational circuits that you build for generating your next state. This register is the memory that stores your next state. Your combinational circuit, your output logic is your combinational circuit generating your output. Now let's look at this in our midterm, right? How our midterm look like. I'm just saying it off the top of my head. So if you a little summary there, please so that should be right. I like to separate them because this is how the implementation in VHDL will be done, right? Combinational circuits will be implemented differently when it comes to architecture level than our memories. Understand? Now we have our output logic. Output logic there. Brought out Y out. That's the only thing that it is. Now we look at this one. So this is our next. Now this thing produce A, B, and C. So not really A, B, and C. The flip flops, right? We had three flip flops. Like we had a combination circuit in three flip flops. Your state was A, B, C. So imagine like your state, no. So 001 thing. This is how I'm describing it, right? Produce A, B, and C. This is our state register. In our case, our state register was stops. Like, it was just three the other way together. And let's do the division like this. Just to grasp. Wow. Okay. This was T, A, B, and the T flip flop for E, B, and C. So what was happening was feeding this one, was also feeding this one. Hope you get this. Now your next state was dependent on what your previous state was. Right? So state 2 will be feeding will be feeding you, will be feeding you. And not only dependent on those things, also dependent on what the value of X was. This one, the output logic was also dependent on A, E, you understand? So now this is a very, very fine machine that we have, you understand? This, this represents next state. Now, this, all the three values they represent are current state, you understand? So this is how the method, so this is how we implement it. Like, implement our output logic, implement our next state logic, implement our memory also. Oh, not forgetting the clock. The clock is very, very important. Clock. So now this is how we implement it. So that has been VHGL in like 10 minutes or 20 minutes. You understand? Join us next time for the 10 part, right? So that we'll be able to come to VHGL. For this one, I was rushing a lot. You don't understand the things for the second one. I'll break down the second one down very, very soon. Now let's look at how the system would look like, partitions, like how our system was. What we'll do is that we'll have, let's look at architecture because the entity is always have to like, right. If I tell you that, oh, this is my system, how would you write the entity? Very, very simple. For let's look at architecture, right? The SSM SSM is this. Look at this. We'll have to first we'll write code for combinational circuits. Combinational circuits to understand. So how we do this is to start now process. What the process like? What it works on, right? What's the sensitivity list? Yes, the list of it. So I don't really know what to do. Next time we'll actually have the question at hand. I like this will be something like this. So we'll begin it. Have some three dots to represent what will happen or end up process. Now we also have to talk about the sequential part. So that process. So for this one, what's happening is that we want to output by out. That's what the combinational is for. And then also want to output, want to also output the, um, the next, right, C plus 1, C plus 1, C, and where C plus 1 represents the next. Because if T is the current, then plus 1 talks about the next T. Now for the sequential part of our process, we'll have to do it like this. Sequential. And this one, it will work on the clock and reset. If you decide that C flip flop should have a reset, this is what it will work on. Depends on your. I will look up again. Right now. Now look up again. And then, so what I want to output? I want to output your like want to output your current state. Right? So want to output your AT. The C. Understand? Current, D current, C current. Particular process. Finally, and our architecture. That's all. This is what I would put it. You understand? So this is the tool. Next time we look at the actual Boolean expression here for Y out PT. So this one will output this one, and then the output is based on memory. Understand? So we implement some key flip-flops inside and the storage. That's how the storage will work. Understand? So that's how it will be. If you look at it, I see it looks very, very simple. But we will access and other some numbers there for you. Thank you so much for joining us.